Hi, everyone. Today, for this live stream, I'm just going to continue where I left off on Wednesday's live stream in terms of solving problems. And we actually did part of question number two. And so I'm just going to continue with what was remaining and also do question number three. And after that, this should take care of like covering all the, well, not even covering, but practicing all of the stuff that's on the assignment for this week. Okay, so let me just remind you of where we left off and pick up from there. Okay, let me take a look in the chat here and my monitor here. Everything looks good. I assume you can hear me. If you can't, then I think you'll let me know because you'll see my lips moving, but you won't hear my voice. All right. So let me remind you of the problem that we left off with. It was this 13-kilogram box on a flat tabletop the tabletop had a coefficient of kinetic friction of 0.25. And that box was attached with a string to a 6-kilogram box, which was dangling off of the end. And I said, let's find the acceleration of the system, and we completed that. Okay. And for part B, I said repeat this, but now let's assume that there's more friction and the system doesn't move at all, so there's no acceleration at all. And I said, okay, now find the coefficient of static friction. Now the question is, I mean, it is worded correctly, but really you're not going to get one value for the coefficient of static friction. You're going to get a range, and that's because static friction, has to ensure that the object doesn't move. And so if you have, a certain amount of coefficient of static friction, it won't move. Anything above that, it won't move, but below a minimum, it will move. Okay, and so what you wind up getting in answers to questions like this is a range. Okay, and so you like on a test or on the assignment, you'll see 0.75 or something like that, and above. Okay, and that would be like the answer that you're looking for. All right, a range, not a particular number. Okay, so let's start off with 2b here, and so let me switch to the our whiteboard, which is not showing up. Oh, there it goes. Okay, let me draw what you would see in a lab. You've got your tabletop here. You've got your 13-kilogram box like this on top of the tabletop like this. So it's 13 kilograms like that. And dangling off of the end, you've got the 6-kilogram box like that. And they are attached by a string, which goes like that. And there is a pulley here holding the string in place. Okay. And so there's step number one, like draw physically what you would see, and then start to identify the forces. There are two masses here, obviously, that one and that one. And so we have to do each one separately. Each one gets its own free body diagram. And free body diagram just means identifying all the forces that are acting on each mass. We could do either one first, but let's start with the 6-kilogram because I think it sort of shows the difference between static and kinetic friction right away. Okay, and so the first force that you should look at is gravity, and there it is, straight down. And you calculate that using mg. Okay, here I'm going to call that m2 to distinguish it from m1. Okay, so this one is m2 here, and this one is m1 there, like that. Okay, so m2g, well, m2 is 6, g is 10, and so 60 newtons. All right, that's easy enough. All right, is that the only force acting on this? If it were, it'd be free falling. Okay, it isn't. What's holding it up is the string, and so you have a force of tension straight up like this, Ft. Okay, now when this thing was accelerating, we really couldn't say what Ft was. All right, that is for part A, not for this particular problem. But for this, but like for when it was moving, we couldn't say what Ft was because Ft had to be less than 60. And the reason it had to be less than 60 was because if it were bigger than 60, then the box would be accelerating up, and it's not doing that. And if it were equal to 60, then it wouldn't be going anywhere, and so it had to be less than 60. But this time, we do know what it's going to equal. Okay, it's got to exactly cancel the force down like that. These two have to exactly cancel one another. Okay, Otherwise, it would accelerate, okay? And so that makes these static friction problems actually easier because you know that the forces have to cancel, and so you can identify more forces that way. Whereas last time we really couldn't identify what Ft was without, I mean, going through the equations. Here we can say right away that Ft's got to be 60 because it's got to balance the force of gravity, okay? And there are no other forces acting, all right? So there we go, we've got that. We've got the free body diagram for the 6 kilogram. Let's take a look at the 13 kilogram. So it has a force of gravity down. This one's mg, but m is now m1g, okay? And that's going to equal 13 times 10, so I'm just going to write that down, 130 newtons, like that. And there we go. There's the force of gravity. There is the normal force up, like this. And there is a frictional force back this way, okay? It's actually static friction, so Fs. All right. And there's tension this way, Ft like this. And let's see if we can identify these values, okay? So the first one you might look at, doesn't matter what order you go in, but the first one you might look at is Ft, and Ft has to equal that Ft, okay? And that's by the third law, Newton's third law, okay? Mediated by the pulley there, all right? So another way to think about it is the tension has to be the same throughout the string, okay? So that's equal to 60 newtons, okay? And we can take a look at the normal force next. That one is going to equal 130 newtons. Why? Well, it has to balance against this one down here. Okay, that's the balance against gravity. And so, Fn has to be 130 newtons. And then we have the force of static friction. And let's think about this. Let me use a different color here. The 130 newtons up will cancel the 130 newtons down. Okay, great. The 60 newtons to the right has to cancel 60 newtons to the left. Why? Well, because if it didn't, once again, the box would move. All right. So Newton's first law says if this box is not moving, all the forces have to cancel out. And so if you've got Ft 60 newtons to the right, you're going to have Fs 60 newtons to the left there to cancel out. And there are no other forces acting on this. Okay. And so I think you can see that the static friction is actually easier. All right. So let me see if there's any questions with that. Okay. Is everyone okay so far? I'll actually type it as well. All right. So if that's the case, then let me switch back to my other whiteboard here. And I don't have to write down all of the forces because all we really want is this coefficient of static friction. Okay. And so let's take a look at what we need. The coefficient of static friction. The formula for that is bigger than or equal to the force of static friction divided by the normal force, like that. All right. So again, as I said earlier, you can't actually determine the exact value for static friction. All you could say is that it's greater than a certain amount. Okay. And from the diagram, we had that the force of static friction was 60 newtons, and the normal force was, what was it again? 130. Yeah, 130. Okay. So it's 130 newtons, like this. And what's that equal to? I don't know. We'll find out. So 60 divided by 130. 130 equals. All right, I'll keep 3 decimals here. There we go. 0.426. All right. So that was that should have been straightforward, okay? So I think you'd agree that that was easier than the previous one, where there we had F net, but it wasn't equal to 0. And because F net wasn't equal to 0, what we had to do is we had to carry this like ft along, and then we had wound up with two equations and two unknowns, and that had to solve that. Here, because f net is zero everywhere, we can identify all the forces, okay, because they have to be such that they're all equal to zero. All right, so if there are no questions with that one, let me move on to the next one. And actually thinking about this, even though, whoops, I kind of figured I would, but that's all right. I know what to do. Um, uh, Even though I put part B first, let's actually do part B before part A, and I'll tell you why afterwards. Okay, so let me read the whole problem, and then we can do part B first. Part B is the static friction one, and the static friction is easier than the kinetic friction. So let's ease our way into the kinetic friction. This question number 3 is about as hard as I would give them to you. Okay, it's fairly involved, and so I think maybe taking a little bite out of it first by doing the static friction first might be easier than going directly for the kinetic friction. All right, but let me read the problem. So we're going to repeat 2A. In other words, we're going to repeat the same problem as before, but this time the 13 kilogram box is not on a flat table. It's on a table which is inclined at 30 degrees. Okay, and it's inclined in such a way that the 6 kilogram mass, the dangling mass, tries to pull the 13 kilogram up the uphill. Okay, and I want for part A, I want the coefficient. I want to find the acceleration, and this time I'm telling you that the coefficient of kinetic friction is 0.025. It's actually 1/10 what it was before. You'll see why when I finish that problem. Okay, and part B says, okay, you got the exact same setup, but for some reason there's more friction. Maybe it's a different table or something like that, or a different surface. There's more friction, and it's not going to move, so there's no acceleration. And so I want the coefficient of static friction. So when you're doing coefficient of static friction, the logic actually goes backwards. It's not that you're trying to find the acceleration. Rather, you know what the acceleration is. It's 0, all right? And as a result, for both boxes, and as a result, F net is equal to 0, okay? And what this does for you is exactly what I showed you a minute ago. It allows you to simply say, oh, all the forces have to add up to 0. It allows you to identify more values for the forces, okay? So let's do part B first, all right? So just to get this clear in our head, the 13 kilogram box is on an inclined plane, all right? And it's still attached by a string to the 6 kilogram box dangling. All right, let me see if there's any questions in the chat there. Nope, we're doing good. All right, so let me switch to the other whiteboard, and there we go. We'll start over. Draw the picture from the beginning. There is the inclined plane like this, and there is the 13 kilogram box there like that. Oh, I'm terrible at drawing. All right, here we go. All right, like that. And here is the 6 kilogram dangling, and we have a rope which comes around like that. Okay. Okay. So you can see that the 6 kilogram, that's this one, is trying to pull the box uphill. It's trying to pull the 13 kilogram uphill. Okay. And the reason I emphasize that is because if I just say the table was tilted, you could have this other situation here where the table's tilted like the other way, in which case the 6 kilogram would be actually pulling the box downhill. Okay, so no, that's not what we have. Okay, what we have is the 6 kilogram trying to pull the 13 kilogram uphill. Okay, so this is what you would physically see in the lab, and now let's do all the forces on it. Okay, so let's start off with the 6 kilogram mass first, do the free body diagram for it, for obvious reasons, because it's only got two forces, and it'll immediately allow us to identify the tension, just like before. So we have the force of gravity down, that's m2g, and nothing changed. The values didn't change, so this is still going to be 60 newtons. Okay, like that. Okay. And we have this force of tension up like this because of the string, and that has to be, once again, 60 newtons. All right. So why is it 60 newtons? Well, because these are the only two forces. They have to cancel. If they didn't cancel, there'd be an acceleration. There's no acceleration, therefore they must cancel. Okay, Great, that takes care of the free body diagram for that one. Let's do the free body diagram for the 13 kilogram and start off with gravity. So we're going to have a component this way, and we're going to have a component that way. Okay, so just to explain, yeah, gravity, I know it's straight down. Okay, but we're going to take out that force straight down, and we're going to break it into its component pieces because we need to add the forces. We need to add all the components, and so we need to break it up into its parallel and perpendicular component. So this one is equal to, this component is m1g, and for the perpendicular it's cosine. Okay, and if you want to know why it's cosine and not sine, I explained that in my pre-recorded lectures. Okay, and so let's see what that works out to. Let me do it on my calculator very quickly here. It's 13 times 10, which is 130, multiplied by the cosine of, and I think the angle was 30 degrees. Let me just check. Yes, it was 30 degrees. Okay, so cosine of 30 degrees, and that gives me 112.58. I'm going to round it off to 112.6. So 112.6 newtons. Okay. This other one, if this one is cosine, then the parallel must be sine. So it's also m1g sine theta. And sine of 30 degrees, that's maybe one of those values that you should memorize. Sine of 30 degrees is a half. Okay, so it's going to be half of 10 times 13, so it's going to equal 65. So this component is equal to 65. All right, newtons. Like that. Great. There we go. We've got gravity. Now, the normal force is, well, so let me just show you a mistake first that some students make. Some students, like, they always think normal force is up and they'll draw it like that, and that is wrong. Okay, the normal force is normal perpendicular to the touching surfaces, and the touching surfaces are here. It's slanted, and so is the normal force. It's perpendicular like that. All right, and Fn is equal to, well, it's got to balance that one, right? Because there's going to be no acceleration perpendicular, and so that one's equal to 112.6. Okay, newtons. Great. The next one is the tension. We'll do friction last. The tension is this way, and the tension, Ft, what's that got to equal? Well, that's got to equal to 60. Okay, so that's equal to 60 here, like that. 60 newtons. All right, and we've identified everything except for friction. Okay, so let me show you what's going to happen here before I write down the friction. All right, pretend for a minute that these were the only forces that are acting. Okay, just these four components here, like that. Okay, so what you would get is, I don't know, what color should I use here? Let me use light blue. Will that work? Nah, it doesn't show up well enough. Okay, so I'm going to use purple here. This one cancels that one, right? We said that already. Okay, and so there's just going to be these two remaining. This one is 60 and that one is 65, and you go, uh-oh, they're not balanced. They have to be balanced, because if those were the only two remaining forces, then gravity downhill would win. It would win by how much? By 5 newtons. Okay, and so in order to keep this box from not going downhill, you need an extra 5 newtons uphill. All right, and you go, well, where's that 5 newtons uphill going to come from? That's the static friction. Okay, so over here you have the force of static friction uphill like that, and you say, how big does it have to be? It has to be 5 newtons. All right, and why? Well, use a different color here, because you now have 60 plus 5 uphill and 65 downhill. They cancel. Okay, so there's the static friction problem. All right, and you could see that what I'm doing here is I'm just making use of the fact that F net has to equal 0 all the time, all the way to the very end when I identify the force of friction as 5 newtons. All right, so that's it for the diagram. The rest is just plugging into the equation. So let me switch to this. All right, and so just to remind you, what we found here, we found that the force of static friction was 5 newtons, And the other one you're going to need is the normal force, and the normal force was 112.6 newtons, like that. And you go, all right, what do I do with those two? Well, the coefficient of static friction is bigger than Fs divided by Fn, all right? And so that's going to equal 5 newtons divided by 112.6. And let me pull out my calculator here. 5 divided by 112.6. It looks like 0.0444. Okay, so there you go. There is the answer to part B, all right, which is what is the coefficient of static friction. I can't, like I said before, I can't tell you the value, but I can only say that it has to be bigger than that value. All right. If it were like zero point 0.1, it won't move. It's like if it's like 1, it won't move. 2, it won't move. A coefficient of 100 won't move. Okay. But if it's less than 0.0444, then it would move, and we're not in the situation of static friction. All right. So is everyone good so far? All right. I'm not seeing any questions in the chat here. And so let me continue. Let me continue. All right, now let's go back and do part A. All right, so again, why did I do that? Well, I did it just because this was the easier one. And now that we have this diagram in our head, the diagram for part A is actually very similar to part B. It's just that there's going to be some unknowns in there. And that's kind of annoying when you have a lot of unknowns. So, you know, I thought it was better to do static. Okay, the other thing is, why did I choose why did I change the value of the coefficient of kinetic friction? Why did I make it 0.025 here? And the answer is, and this is something you'll see in the lab, I didn't even mention it in the pre-recorded lectures, but the coefficient of kinetic friction has to always be less than the coefficient of static friction. And you go, why is that? Well, I mean, just from a physics point of view, from like a heuristics point of view, things will just sort of be stuck in place until they get kind of a little push, and then they start to move. And not only do they start to move, they'll actually accelerate a little bit, okay? So there's kind of like an initial impetus to get over the hump, to get them to move, and that's why static friction is just a little bit bigger than kinetic friction. Well, in part A, or sorry, in question number 2, I had that my kinetic friction was 0.25, and that has to be less than what I found in this question, which is 0.044, and well, that didn't work, okay? So I actually discovered this mistake because I was doing this problem for my Physics 111 class, and I go, wait a minute, something's wrong, and I immediately realized that I just used the wrong, like when I make up these problems, I just make up numbers, and sometimes I make up numbers which are not physical, and unless I do the problem myself, I won't know that maybe I chose a number which doesn't make sense. So 0.25 doesn't make sense. You have to actually make it smaller than that. So I just mentioned that in passing, okay? So, all right, let's go back to part A here. And in part A, we have the same situation, but now it is moving. And there is a coefficient of kinetic friction of 0.025, okay? And we want to find the acceleration. So I didn't say that, but I should just say here, find the acceleration. All right. So how do we do that? Well, let's start with a picture. Okay, so the picture is going to look a lot like this, but this one's a little bit too messy now. You know, it's hard for me to rub off things in this particular, um, what is it called, the graphics editor. So let me just start over. Okay. All right, so here we go. We've got our table, which is on a slant, our inclined plane. We've got our box here like this. Okay, we've got our dangling box here off of the end. We've got our string, which goes up and around like that. Whoa, doesn't look right. All right, like that. And we've got our pulley to hold it in place like that. Okay, this is obviously the 6 kilogram, and this other one is the 13 kilogram. Okay, so now what? Well, we'll go through the forces again, free body diagram for each one of them. Start with the 6 kilogram because it's easier. and we know this is 60 newtons. Okay, so you go, why? Well, nothing changed from the previous. Okay, in the previous diagram, you know, it's M2G, and here it's M2G, so it's still 60 newtons. The tension up, though, we don't know. Okay, and the reason we don't know the tension up is because this is going to move. Okay, and in fact, maybe we should switch back just for a second to the other diagram. Yeah, this one right here. So let's take a look at this one for a second. Okay, you see the green, the force of friction here in green. Okay, imagine that weren't here. Imagine that weren't here. What you would have is you would have 65 newtons downhill and only 60 newtons uphill. This box wants to slide downhill. Okay, so if we go back to this one, the situation that we're in here is that if we don't have any friction at all, this one is going to want to accelerate up, and this one is going to want to accelerate downhill like that. Okay, so you say, well, wait, I don't see that. Well, again, you know, if there were no friction, remember in the previous diagram, the friction was uphill. If you turn off that friction uphill, what was going to happen? What was going to happen is the force downhill here would be bigger than the force uphill, and it would slide downhill. And so we know before we even do this problem that this box is going to slide downhill, okay? Because there's going to be less friction than there was in the static case. There's still going to be some, but there's going to be less friction. And so it's not going to be enough friction to hold the box in place. And if you turn the friction off, it's going to want to slide downhill. Okay, so there we go. I'll show you another way that you can reason that. But here, that means that Ft, we don't know the value. And in fact, whatever Ft is, it has to be bigger than 60. Why? Because it's got to accelerate the 6 kilogram box uphill. Okay, so that was a little bit complicated, but I'll come back to this at the end, and I'll show you why that acceleration has to be in that direction, and then just realizing that the acceleration is up, that means that this, I don't know its value, but I do know that it has to be bigger than that. Okay, it could be like 65, it could be like 63, I don't know, but it has to be bigger than 60. Otherwise, the box would not accelerate uphill. Okay, so great. We're done with the free body diagram for the 6 kilogram. Let's do it for the 13 kilogram box. There's a component of gravity this way and a component of gravity that way. Mg cosine theta, all the values are the same, so it's the same number, 112.6. Okay. And this one is mg sine theta. All the values are the same, so this one is 65 newtons. Okay. We've got our normal force this way, and that one has to be 112.6. All right. And we have tension up like this. And we don't know how big it is. All right. And we have the force of friction, and I don't know how big it is yet. We can calculate it. We'll do that in a minute. But we also know that it has to be up, okay? And this time we're going to call that FF, because that's what I've been calling the force of static friction. We don't know how big this tension is because it's equal to the other tension. Like the tension throughout the string is the same, okay? So if you don't know the tension here, you don't know the tension there, okay? All we know is that they're the same value, but not what that value is, okay? For the force of friction, this is kinetic friction, so we can calculate that. I just don't have enough room to do it here, so I'll do it on my other whiteboard, okay? But I did say that I was going to come back to why the acceleration is up. If you forget all the other forces and just look at two forces that are going to be competing, like all the internal forces will eventually cancel. The two forces that are going to be competing is, like, this one wants to pull the whole system in the direction that I drew A, okay? And this one wants to pull everything in the opposite direction. In other words, this one wants to pull things this way. Not only the 13 kilogram box, but also the 6. And this one wants to pull everything in the other way. So it wants to pull the 6 kilogram down, and it wants to pull the 13 up. Well, which is the bigger? The 65. And that's another way to see, just sort of roughly, just to reason out, that the acceleration is going to be in the direction that I drew it, okay? So let me rub off all those construction lines, whatever. Okay, there we go. And so there's the diagram. I do know what this value is. Well, I mean, I can calculate it, but I just don't have enough room here. Okay, so let me switch to my other um, screen here like that. Okay, and let me go through the two. So I've got the M1 here, and M1 is the 13 kilogram box, and we had the parallel mg, and that was equal to 112 points. Sorry, no, that was the 65 newtons. We had the perpendicular force of gravity, that was 112.6 newtons. I'm just transcribing from the from the diagram. The normal force was 112.6 newtons as well. Okay. The force of static friction, we don't know it yet, but we can calculate it because it's equal to the coefficient of kinetic friction multiplied by Fn. Okay, so remember, kinetic friction, it's actually an equality. And so you can use this formula to get FF. Static friction, it's an inequality, and so you can't use an inequality to solve for a number. Okay, equality gives you a number, an inequality will give you a range. All right, and so what's that equal to? Well, that's going to equal to 0.025 multiplied by 112.6. And let me use my calculator to quickly calculate that. So 112.6 multiplied by 0.025 is this number here like that. Okay, so I'll keep an extra. Usually I keep only 3 significant figures, but I'll keep another one. All right. Okay, and then the other force that was acting on the 13 kilogram was tension, and we don't know what it is. Okay, and then for the 6 kilogram, we only had 2 forces. We had mg down, and that was 60 newtons. I guess I should be calling this m1g and this one m1g to distinguish it from m2g. Okay, and then there was the tension up. Oops, ft up, and we don't know how big that is. All right, so that's just transcribed. All right, see if there's any questions. Nope, good. All right, now what? Okay, so here we do have an acceleration, and so we identified all these values so that we can get that acceleration, and we get that acceleration through F net. Okay, and same thing here. There's also an F net for both of them. All right. All right, so how do we get this F net? Well, we have to do the vector sum of all these forces. So it's probably a good idea to look back at the diagram, and let's look at the 13 kilogram first. What forces are going to cancel? Well, this force here, the normal force, is going to cancel gravity perpendicular. All right, and this force here, it's not actually going to cancel the other two, but it's competing with these two. Okay, so you've got 65 newtons down minus the tension up minus the force of friction up. Okay, so the 65 will eventually win, and we know that because it's going to be accelerating downhill here like that. Okay, so we know the 65 will win, but it's not going to, it's still going to be decreased by whatever Ft is and decreased by whatever Ff is. Okay, and so for the switch back here. So for the net force here, we're going to say, okay, it's going to be that 65 newtons, that's this one here, okay, and we could even say down, all right, minus the force of friction, and this was up like this. It's going to be minus 2.815 newtons, okay, and it's also going to be minus the Ft, all right, because that was also uphill like that. All right, and let me just quickly reduce that. So let's say 65 minus is going to be that, okay, minus Ft. All right, and since we don't know Ft, we can't go any further. All right, that's it right there. That is our F net as good as we can get it at this point. And we're going to use that in Newton's second law. Okay, remember we're going to the acceleration, and to get to the acceleration you go through F net, and here's the formula that connects F net to ma, all right, to a, okay, and it's m1a because again we're talking about, you know, the 13 kilogram, okay. And so for F net we're going to write in this expression. Again, we can't do any better because we don't know ft yet. All right. For m, we're going to put in 13 because it's m1, and then a. Okay, so there's equation number 1. Great. That's it for that one. Let's go back to the diagram because now we want to get f net for number 2, and to make sure we get the the directions right here, like which is positive, which is negative. So let's look at the diagram again, and now we're looking right here. Okay, which one's going to win? Which force is going to win? Well, it's accelerating up, so that one is the winner. Ft is bigger than the 60. I said that before, but just to remind you, Ft is bigger. And so F net here is going to be Ft minus the 60. All right, so Ft is up and 60 is down, so it's going to be Ft minus the 60, and that's going to equal A. All right, so over here, we're going to get Ft minus the 60, and that's got to equal, well, that's it for that one. And then using the second law, so like this, maybe I should just label it here. That's the second law, Newton's second law. Okay, so we got the same thing again. All right, whoops, Newton's second law, but this time it's Newton's second law applied to M2. All right, and we can substitute in here. We're going to have Ft minus 60 there like that, and that's going to equal what? That's going to equal 6 times A like that. Okay, and there's our equation number 2. All right, good so far? So now what? Well, we got to solve. So we're going to take this equation, and we're going to take this equation like that. All right, and we're going to add them together. So you're going to get this plus that, okay, is going to equal 19A like that. And so the FTs will cancel like this. And 62 minus 60 is going to equal that. So that is equal to 19A. And A is going to be a tiny number. A is going to equal, let me do it here. Whoops. It's going to equal this tiny number right there like that. Okay? Meters per second squared. All right. So there you go. Oh no. Guys, I'm sorry. I've been working on, I for some reason it didn't switch over to the other scene. Okay, I apologize. And no one mentioned it in the chat here. Okay, so let me make sure that this switched over. So as I was doing the calculation, what happened was I was actually on the wrong screen. That's okay. Let me just repeat it very quickly, what was going on here. Okay. My setup isn't the best, but no, we'll go. I mean, that's all I have right now. Okay, so let me just go very quickly over what happened here. I had, these were the forces as identified, okay, for M1. All right, so I had that F net has to equal the 65 up minus the 2.815 down minus FT down, and that reduced to 62.185 minus FT. And now we're going to use that, and F net is equal to M1A. All right, so there's the 62.185 minus FT, and that's going to equal M1, which is 13 times A, like that. Okay, great, and that gives us equation 1. For equation 2, okay, we had that F net is going to equal, F net is going to equal the FT up minus the 60 down, okay, and so that's going to give me F net, which is FT minus 60, equal to M2A, which is 6 times A, and that's our second equation. So here's our equation number 1. Here's our equation number 2. Putting the two equations side by side like that, okay, we can just add the right-hand side of both of them, and that's got to equal to the sum of the left-hand side on both of them, and that turns out to be, here, let me just do that very quickly. It's this one plus this one. Whoops. And that's got to equal 13 plus 6, which is 19a. Notice that the FT's cancel. All right, so the FT's cancel, and you get what I have right there. Okay, and so um, what we get now is 2.185 is equal to 19.8, or that A is equal to 0.115 meters per second squared. So it's very small, but there is some acceleration downhill. Okay, so let's look back at the diagram very quickly. So that FT, we do know its value now. That FT is, let me just look here what the FT was. FT was 2.815. So over here, FT was equal to 2.815, like that. And the only thing we didn't know was the FTs there. All right, and the question was for the acceleration, and the acceleration turned out to be 0.1185. All right, so that ends our that ends the lecture. All right. If there's any questions on what I did right now, or if you have any questions on the assignment, feel free to ask me. Otherwise, tonight at during my office hours, during my Google Hangout, it'll be the last question, last opportunity that you'll have to ask questions about the assignment. All right. So if there are no more questions, then we're done. Let me just chat here. Any questions? If not, we're done. All right, well, I'm not seeing any questions, so let me just say goodbye then, and I'll cut the chat. All right, bye-bye, everyone.